Hello, everyone. I would like to start by thanking the organizers for giving me the opportunity to speak at the Knots and Links in Dimensions 3 and 4 topic session at the Nearly Carbon Neutral Geometric Topology Conference. So today I will be talking about Chebyshev polynomials and how they're related to Skein modules. And in particular, we will see that Chebyshev polynomials give us a nice presentation of handle sliding relations that appear in the Kaufman bracket Skein module. So what are Chebyshev polynomials? They're primarily of two kinds. They both have the same recurrence relation, just the initial conditions differ. So for the first kind, we have T naught D equals 2, T1 D equals T. For the second kind, we have S naught D equals 1, S1 D equals T. And Chebyshev polynomials are related to two trig functions. And so these two equations over here give us how these polynomials are related to trig functions. So in this talk, we will see that handle sliding relations in the Kaufman bracket Skein module of the connected sums of handle bodies can be written in terms of Chebyshev polynomials of the second kind, which is a rather surprising connection that Chebyshev polynomials have with the Kaufman bracket Skein module. So what are Skein modules? So we have all of our polynomial link invariants: the Alexander polynomial, the Jones polynomial, the Home-Flapetti, Kaufman two-variable, the bracket, the Dubrovnik polynomial, and the Vasilyev-Gosarov finite type invariants. So all of these invariants are links in S3, and they all have some defining Skein relations. So if we want to build invariants of links in any arbitrary three-manifold and not just the three-sphere, based on Skein relations, then this is where Skein modules come into play. So Skein modules are three-manifold invariants and link invariants, and they were introduced by Josip Plutitsky in 1987 and independently by Vladimir Turaev in 1988. And there are many different Skein modules that you can associate to a three-manifold. And the reason for this is that you can take links in your three-manifold to be either up to homotopy or isotopy or oriented or unoriented, and so on. But what all of these different Skein modules have in common is that they all try to say something about the three-manifold to which they're associated based on the kind of knot theory that it admits. So Skein modules are essentially generalizations of all the various polynomial link invariants in the three-sphere to arbitrary three-manifolds. And since we're moving away from the three-sphere to an arbitrary three-manifold, we also need to move away from the usual knot and link projections and diagrams that are used to define polynomial link invariants in S3. And we do this by considering links to be identical outside of a three-ball in the three-manifold that you're working with. And inside the three-ball, they appear as various prescribed tangles. And for us to be able to distinguish links from one another based on their local appearance in the three-ball, we will work with oriented three-manifolds. So why are Skein modules important? Why has there been a flurry of activity in the last 2 decades or so in their study? Well, the reason is that Skein modules have intricate connections with many fields of mathematics, for example, algebraic geometry and hyperbolic geometry via SL2C character varieties and quantum type Miller spaces. They appear in one of the definitions of the Witt-Reshetkin-derived three-manifold invariants. They're related to TQFTs, quantum cluster algebras. You can categorify Skein modules to obtain homological invariants of three manifolds, similar in spirit to, say, Khavanov homology. And more recently, there have been connections discovered with mirror symmetry. And in particular, there are certain conjectures which pertain to Skein algebras, which have been resolved using tools which come from mirror symmetry. So with this motivation, we're ready to define the Kaufman bracket Skein module, which is the Skein module that we'll focus on in this talk. So what we do is that we consider formal linear combinations of ambient isotropy classes of unoriented framed links in M. So essentially, we have a free R module, where R is a commutative ring with unity, is an invertible element in R. And what we do is that we mod out by the submodule, which is generated by these two relations. So we have the trivial component relation, and we have the Kaufman bracket Skein relation. And once we mod out by these two relations, what we get is the Kaufman bracket Skein module. Keeping in mind that our manifold is oriented, we work with a commutative ring with unity. And this element over here is the trivial framed link. So One thing is that the KBSM has a framing relation, which arises due to the fact that the Kaufman bracket polynomial is not invariant under the first Rademacher move. And so we have this relation L1 plus A cube L, where L1 is obtained from L by twisting its framing by one positive full twist. And primarily for this talk, we will focus on the ring of Laurent polynomials, in which case we will use a simpler notation for the KBSM. So here is an example of the KBSM of the thickened annulus or the solid torus. So we have this link, and we can resolve this crossing using the Kaufman-Brackes-Skein relation. And we can use the trivial component relation to simplify to get this element in the KBSM of the solid torus. So X over here is the homotopically non-trivial curve on the annulus, and this over here denotes the empty link. Okay, we can also work with relative Kaufman-Brackes-Skein modules, in which case we have an oriented three-manifold with boundary, and we have certain number of framed points on the boundary. And in this case, we have relative framed links which connect these frame points with one another. And then you can mod out by the Kaufman-Brackes-Skein relation and the trivial component relation, and then what you get is a relative Kaufman-Brackes-Skein module. And as a note, the RKBSM over surface times an interval has an algebra structure which is similar to the Tempedi-Lieb algebra. So here are some properties of the KBSM which are pertinent for our talk. So these are due to Josip Kriticky from 1987. The first one says that an orientation-preserving embedding of three manifolds yields a homomorphism of their KBSMs. The second one says that if you have one manifold which is obtained from the other by adding the three handle to it, then the associated embedding yields an isomorphism of the KBSMs. The third one says that if you have one manifold with boundary, and it has a simple closed curve gamma on its boundary, and then you have n, which is obtained from M by gluing a two handle along the simple closed curve, then the associated embedding yields an epimorphism of the KBSMs. And in particular, the kernel of this epimorphism is generated by two handle sliding relations. So an orientation-preserving embedding yields a homomorphism, three-handle addition yields an isomorphism, and two-handle addition yields an epimorphism of KBSMs. And so what all of this gives us is the following. We can find the KBSM of any compact-oriented three-manifold since such a manifold is obtained from a handle body by adding two or three handles to it. And so the generators of the KBSM of that manifold are going to be the generators of the KBSM of a handle body, and the relations are given by two handle sliding relations. And the KBSM of a handle body is actually not that complicated. So we think of handle bodies as thickenings of planar surfaces. And in 1987, Josip Kriticky showed that the KBSM of a surface times an interval is a free R module generated by the empty link and links in F which have no trivial components. So the problem of finding the KBSM of a compact-oriented three-manifold gets reduced to computing the KBSM of the handle body from which is obtained. And then it's only a question of computing the handle sliding relations which occur due to two handle addition. And the generators are exactly the generators of the handle body. Another theorem due to Josip Kriticky from the year 2000 involves the KBSM of compact-oriented three manifolds, their connected sums. And this theorem is for the field of rational functions. So the theorem states that if you have the KBSM of the connected sums of two compact-oriented three manifolds, then you get this nice tensor product of the individual KBSMs. However, this theorem is not true when you work over the ring of Laurent polynomials, and this is something important that we'll see later on in the talk. Okay, so this brings us to Witten and Marchier's conjectures. So here are some examples which will give an idea of what Witten's conjecture is. So Jim Hoste and Josip Kriticky computed the KBSM of length spaces, and they show that it's finitely generated over the ring of Laurent polynomials, and it has the floor of P by 2 plus 1 P generators. Later, in the next year, they computed the KBSM of S1 times S2 and show that it's infinitely generated. And in fact, it has this nice decomposition into free and torsion modules. And this decomposition arises exactly due to the presence of this non-separating two sphere in S1 times S2. In 2016, Carrega computed the KBSM of the three torus over the field of rational functions and showed that it's finitely generated with 9 generators. And later, Gilmer showed that these are linearly independent, hence forming a basis. And then in 2019, Cherry and Wolf computed the KBSM of a compact closed-oriented surface times an interval, and the genus of the surface is greater than or equal to 2. And they show that it's finite dimensional over the field of rational functions with dimension 2 raised to 2g plus 1 plus 2g minus 1. And earlier, Gilmer and Masbaum had shown that this is a lower bound of the dimension of the KBSM. So the reason why I stated these examples is because it's very clear from here which KBSM is finitely generated, which one is not finitely generated. And the reason is this conjecture, which is attributed to Edward Witten, is now a theorem. So the conjecture / theorem says that the Kaufman-Brackes Skein module of any closed-oriented three-manifold over the field of rational functions is always finite dimensional. And this was proved in the affirmative by Gunningham, Jordan, and Safronov a couple of years ago. However, this theorem is not true if you work over the ring of Laurent polynomials. So for the field of rational functions, the KBSM is always finite dimensional. However, this is not true when you work over the ring of Laurent polynomials. We saw on the previous slide that the KBSM of S1 times S2 is infinitely generated. So the point that I'm trying to make is that more is known about the KBSM over the field of rational functions than over the ring of Laurent polynomials. So to this end, Julian Marchais conjectured the following. He conjectured that the KBSM of closed compact-oriented three manifolds has this nice decomposition into free and torsion modules. And for example, we saw this in S1 times S2. It had that decomposition into free and torsion modules. For any surface times S1, the proof given by Cherry and Wolf shows that the KBSM always has this nice decomposition into free and torsion modules. However, I show that this conjecture is not true in general, and the counterexample is given by the KBSM of the connected sum of two copies of the real projective space. So here is the structure of the KBSM of RP3 connected sum RP3. It has these two copies of the free part. However, this module over here is not, this is not a cyclic module. And in fact, this submodule S is generated by these two relations. And we see that Chebyshev polynomials of the second kind make an appearance in these two relations. So this is the first instance of the Kaufman-Brackes Skein module of an oriented three-manifold, where the handle sliding relations have Chebyshev polynomials appearing in them. And in fact, this was due to Mryczkowski that the Kaufman-Brackes Skein module of this three-manifold does not split as the sum of cyclic modules. So while most examples for which the KBSM has been computed, Marchais' conjecture is true. However, the moment we talk about connected sums of oriented three manifolds, we have an outlier. We don't have this decomposition into free and torsion modules. So if you want to study the KBSM, the structure of the KBSM of an oriented three manifold, the first thing would be to investigate the KBSM for connected sums of three manifolds. And the basic case for that is the connected sum of handle bodies. So in the year 2000, Josef Krititzky stated and published this theorem, which is about the connected sum of two handle bodies, Hn and Hm. And he stated the following. He stated that the KBSM of Hn connected sum Hm is exactly the KBSM of the n plus m genus handle body, modeled out by this submodule, which is generated by two handle sliding expressions of this form. So let's see exactly what these two handle sliding relations are and where they come from. So let's take a simple case where we have H2 connected sum H1. So this is obtained from H3, so the genus 3 handle body as follows. So you take the disk which separates these two toroidal holes from this one, you take the boundary of this disk, and then to the boundary you glue this two handle. And this is what gives us H2 connected sum H1. So the moment we've added a two handle, what we get is that the KBSM will have these two handle sliding relations. And this submodule here is exactly generated by these two handle sliding relations. So ZK over here represents basis elements of the KBSM of the disk with n plus m holes times the interval. And they have no contractible components, and they intersect the disk D, this disk D, exactly k times. And then UZK is exactly a modification of ZK as shown. And where do we get this UZK from? Well, what you do is that you slide this top string of ZK along the two handle to get this diagram. And then you can use the Coffin bracket Skein relation to resolve these two crossings. So this is what gives us UZK. And then resolving using the Coffin bracket Skein relations, we get this coefficient a raised to 6. So he showed that the handle sliding relations needed for the KBSM of the connected sum of Hn with Hn is exactly sliding the top string along the two handle. However, I showed that this theorem is incorrect. The counterexample is given by Hn connected sum Hm, where n plus m is greater than or equal to 3. And we show that the submodule should be replaced by a strictly bigger module, and that the relation in the theorem is not enough. We need more handle sliding relations. So in fact, we showed the following. We show that the natural epimorphism due to the embedding of H3 into H2 connected sum H1 is not an isomorphism. And then we generalize that to all handle bodies where n plus m is greater than or equal to 3. So we show that the natural epimorphism is not an isomorphism. So this brings us to handle sliding relations in handle bodies and how we represent them. So since H2 connected sum H1, or rather any connected sum of handle bodies is exactly another handle body with the two handle attached to it, what we can do is that we can project everything to the underlying planar surface of that handle body. And we keep track of the fact that we have gamma along which our two handle was attached. So in this case, we have H2 connected sum H1, which is exactly H3 with the two handle attached. So we project it onto the disk with 3 holes, keeping track of the fact that we have a two handle attached along this curve gamma. And so we needed a nice way to represent two handle sliding relations for our calculations. And so what we did was that we managed to use the Templey-Lieb algebra and the Templey-Lieb elements as follows. So what we did was that we had a planar surface onto which we projected everything. We have our curve gamma. Then we embed our Templey-Lieb box in a neighborhood of this curve gamma, and inside we have all of our Templey-Lieb elements. And then to these Templey-Lieb elements, we glue any curve system on the outside on the planar surface. And then once we glue this curve system with the Templey-Lieb elements, we get all positive relative curves on this planar surface. And the reason why we did this is because now we can represent all of our two handle sliding simply as Templey-Lieb elements, which simplified our calculations a lot. So this, for example, represents the disk with 4 holes, and this is ZK with the identity element of the Templey-Lieb algebra with 4 points on the left edge and 4 points on the right edge. So that's TL4. And so this element over here is Z4 in the theorem. So now that we have a nice representation of handle slidings, what are the possible handle slidings that you could have? So you have ZK. You could slide the top arc across the two handle over these K-1 arcs to get this diagram. You could slide the bottom arc over the remaining arcs across the two handle to get this diagram. Or you could slide the bottom arc in the opposite way to get the mirror image of this diagram. So there are many possible handle slidings that you could do. And what we showed is that for this curve system in the disk with 3 holes, this curve system gives rise to the counterexample. So what we did was that we considered positive two-handed sliding on the upper arc, we considered positive two-handed sliding of the lower arc, we combined these two relations, and we ended up getting a completely different relation which did not exist in the submodule stated in the previous theorem. So that gave us a counterexample. However, the counterexample was only when n plus m is greater than or equal to 3, meaning when both of our handle bodies are not solid though, right? We had conjectured earlier that the natural epimorphism due to the embedding of H2 into H1 connected sum H1 is an isomorphism. And we were recently able to prove this, joint with Tangley and Josip-Shutitsky, that this natural epimorphism is indeed an isomorphism. And in fact, what we showed is that the KBSM of S of H1 connected sum H1 is this ring, which we extend a little bit, modded out by two-handed sliding relations of exactly this form. So in this case, we exactly have handle sliding where we slide the top string across the two handle in the positive way, as was stated in the previous theorem. Okay, so here's the idea of the proof. We use the relative Kaufman bracket Skein module to simplify our calculations for two handle slidings. So what we do is the following. So we take a neighborhood of our simple closed curve gamma along which we glue the two handle. We place these two marked points on the curve gamma, which divide the curve gamma into two arcs, gamma 2 and gamma 1. And then say we have any relative curve in the relative Kaufman bracket Skein module of the manifold with two marked points, which approach U and V along this fixed tangent. So now if you want to slide this relative curve, that is simply sliding alpha union gamma 2. So that simply replaces alpha union gamma 2 with the curve alpha union gamma 1. So any curve in the KBSM, if you want to slide across the two handles, simply replaces alpha union gamma 2 with alpha union gamma 1. And so if we introduce a homomorphism from the relative Kaufman bracket Skein module to the absolute Kaufman bracket Skein module, given by omega of alpha is alpha union gamma 1 minus alpha union gamma 2, then the image under omega of the generators of the RKBSM form the generating set of all handle sliding relations in the absolute KBSM. So all we have to do is that we need to see what the image of the generators of the RKBSM under omega R, and that will give us the generating set of the handle sliding relations of the absolute KBSM of the three manifold. And so we showed that CLA3, CRA3, C0A3, and C1A3 form a basis of the relative Kaufman bracket Skein module of the disk with three holes times the interval. So CL is this diagram, CR is this diagram, C0 is this diagram, and C1 is this diagram. And then we just had to see what happens to all of these under omega. So we show that negative two handle sliding on the upper arc is spanned by the image of CL. We show that the image of CR corresponds to ring sliding. The image of C1 is 0, and the image of C0 follows from ring sliding. So all that's left to show is that ring sliding follows from negative two handle sliding on the top arc. And this showed us that the KBSM of H1 connected sum H1 is exactly this ring modded out by this handle sliding relation, which comes from sliding the top arc across the two handle. And in fact, very recently, we were able to find the following, which is the handle sliding relations in the KBSM of H1 connected sum H1 are generated by are represented as follows, where Sn is the Chebyshev polynomial of the second kind, and curly k represents the element a raised to 2k minus a raised to minus 2k. So we were able to find this really nice representation of handle sliding relations in the KBSM, and this is sort of reminiscent of the of the relations that we saw in the KBSM of the connected sum of RP3 with RP3. And this is a rather surprising connections that Chebyshev polynomials have with KBSMs, because Chebyshev polynomials are polynomials which are related to trig functions, and you would not think that they could be related to such a topological construct in Skein modules, but they are. So this is work in progress, and it should appear soon. So what are some future directions from here? Well, the goal is to understand the structure of the KBSM. And so the first step would be to generalize this result for the connected sums of handle bodies to the connected sums of length spaces. There are some open questions. For example, what is the structure of the KBSM of Seifert fiber manifolds? What is the structure of the KBSM of Hn connected sum Hm when n plus m is greater than or equal to 3? What are all the handle sliding relations which exist in the KBSM, and are they related to Chebyshev polynomials in any way? So this was my talk. Thank you all for listening. I hope you enjoyed it. Thank you so much.